And so commences the afternoon session. I heard it was a great morning, and I think you'll be very pleased with the afternoon sessions as well as we transition to the search for life. It's really a great pleasure to introduce Andrew Howard, who I've known now for, I don't know, something like 6 or 8 years, maybe something like 8 years, since before the Kepler mission launched. Andrew got his bachelor's degree in physics at MIT, and from there he went to Harvard, where he also got a PhD in physics. So his background is rather eclectic, and you should ask him some questions afterwards about his experience with optical SETI projects. Andrew's PhD thesis was an astronomical search for nanosecond optical pulses, right?
That's right.
Did I get that right?
Yeah.
Oh. And so after that, he got pulled into the field of exoplanet research and went to Berkeley, where he met Jeff Marcy and got totally immersed in the Kepler project. And we worked hard for many years and still continue to do that work of ultra-high precision radial velocities to get masses of exoplanets. So Andrew is the discoverer on numerous really, really interesting destinations like you see on this front slide. He's also an expert in planet statistics, so you can ask him about the demographics of exoplanets in our galaxy. So without further ado.
All right. Thank you so much for that wonderful introduction. I'm really glad to be here. My talk, this first talk of the afternoon, is going to be a little bit of a mix. I'm mixing in some of what I see as kind of the introductory material just to make sure everybody's on the same page. We're talking about planets today, and we're especially talking about transiting planets, and I'm going to go through a few just kind of basic ideas for that. I'm also going to mix in some big ideas. I'm going to mix in some of the latest and greatest results, so I hope that all of you will take away maybe different things from this talk. So I like to think of planets as destinations. This is one destination we might imagine. As Natalie said, my name is Andrew Howard. I'm at the University of Hawaii and just having a nice week-long visit to California. The basic question that I am interested in, and many people at NASA and in astronomy generally interested in, are Earths common? To answer this question, we have to say a little bit about what we mean by an Earth. And that's a lot of what we're here to learn about today. What kind of orbits are Earth-like? What kind of water content is Earth-like? I'm going to be talking for the next 15 minutes or so about a search for Earths using the Kepler Space Telescope. So, as many of you know, Kepler is a 1-meter space telescope. It's in orbit around the Sun. It has been for the past 6 years, Natalie? Almost 6 years. Yeah. And Kepler does an amazing thing. It searches for planets which cross the disk of their star, blocking out a small fraction of the light from the star. And when you record the overall brightness of the star, we see this characteristic dip. From the depth of the dip, we can determine the size of the planet relative to the size of the star. And as these dips repeat, we learn about the orbits of the planet. The repetition time is the orbital period, the time it takes the planet to go once around its star. So, since this is a classroom full of teachers, I thought I would start off by asking you a question. Imagine we have, and there's only going to be a couple questions in today's lecture. So imagine we have a planet passing in front of the star. Here's the star is red, the planet's in blue. The brightness as a function of time, remember we can't actually resolve the star, we just record its overall brightness, it's a light bulb. It goes from 1, some maximum brightness, decreases, and then goes back up. So do we have any volunteers for how to compute the size of the planet?
We use the square root of the areas. You're comparing the areas.
Yeah, so that's exactly the right idea. The size of the dip is just the area of the that is blocked of the star, normalized by the star's full area. It's pretty simple. This is nicely a geometric problem. And so if you imagine that if we just call this 100% light up here, if at the minimum of this transit we record 99% as much light, that's a 1% change, that means this quantity right here is 1%, 0.01. Take the square root of that, that means the planet is 1/10 the size of the star. So this is the kind of straightforward principle that allows us to deduce the sizes of these planets as well as their orbital properties. And these planet sizes are relative to the star sizes, which we think we know pretty well. So Kepler launched about 6 years ago. It's in orbit around the sun. For 4 years, Kepler stared down this Orion spur of the Sagittarius arm of our Milky Way Galaxy. And Kepler, when projected on the night sky, looked up at a 100 square degree patch of night sky. These rectangles here denote the CCDs projected onto the sky. And Kepler surveyed about 150,000 stars at any one time in this 100 square degrees, and it looked for these characteristic dimmings of planets. Here's what it would look like if you could stare at just one star from Kepler. We'll focus on the star right there in the center. Note how the star pulses. This is the dimming. Kepler, of course, can't zoom in like a graphics animator. This is the famous system that Eric Ford showed you earlier in the morning. This is the Kepler 11 system. This has a total of 6 planets, 5 of which are inside the orbit of Mercury. It's a dense and, as Eric emphasized, an extremely flat planetary system. There it is overlaid on the solar system. So we can learn an enormous amount about planets just from these transit light curves. The Kepler data are so beautiful, I want to show you some of it yourself and have you play the role of planet discoverer. This is real Kepler photometry attained over the course of about the first year of the Kepler mission. And each measurement here shows the relative brightness of the star during one 30-minute interval of time. So Kepler measured the brightness of each one of these stars. This is the brightness of one particular star, and you can see that it changes a little bit over time. Note the vertical axis here. The first tick mark is down by, 1/20th of 1%. It's a very small dimming. So the question for you, the teachers, can you discover the planet in this Kepler light curve? Can anybody say what its orbital period is? I give this talk a lot, and I'm waiting for somebody with the laser pointer in the back to just start pointing it out.
Is it like 50 days? 50 days.
50, 60 days? Yeah, that's about right. So here I'll highlight the transits. It turns out it's about 45 days. One transit here, another one here, another one here, another one here. Perfectly regular. If we zoom in on one of these transits, this one right here, we can see that this transit actually has a nearly flat bottom. That means that once the planet passes in front of the star, it's blocking more or less the same amount of starlight until it emerges from the other side. And in this zoomed-in view, we can see that there's actually a second planet in the system. Can anybody see this one? Anyone want to guess its orbital period? Ah, that wasn't me. It turns out it's less than a day, 0.84 days. This is Kepler 10b. The discoverer of this planet was the person that introduced me, Natalie Battaglia. And Kepler 10b has many remarkable properties. One of them is this incredibly short orbital period, less than a day. The other is that these dips are incredibly shallow, meaning that the planets themselves, the planet itself must be very small. And so if we phase fold this data, if we were to imagine taking this graph and just folding it on top of itself, and pile up all the data, you can see that indeed, every single time, literally hundreds of times, this planet passed in front of its star, it always went low when it was supposed to. And the depth of this dimming is only about 150 parts per million. Since we know the size of the star, we can translate that into physical units, and it's about 1.4 times the Earth, 40% bigger than the Earth. Yeah, question?
It's a naive question, but how do you distinguish this from some sort of internal phenomenon of the star, which is that its luminosity varies according to some regular time interval? Why are you convinced that it's a planet and not some regular burp?
Good question. So we know a lot about how stars oscillate. In fact, they ring like bells. And you can, if you were to strike one side of a star, even though it's kind of a tenuous gas atmosphere, that would propagate to the other side, bounce back, and it would ring back and forth. And we actually see these seismic waves in stars, and we use them as a diagnostic. We know that they have characteristics which are related to the entire surface of the star. So we don't see these very short duration kind of box-shaped-like curves. We see rather a sum of sinusoidal-like disturbances. So that's the main difference. Another thing which could potentially fool you is you could imagine having a dark spot on the surface of the star which rotated into your view and then rotated out. This is what a star spot is. We actually see those also with Kepler, but we know what the rotation periods of stars are. They're typically weeks and months. We also know that when we see these star spots, that again, they don't produce this kind of box-shaped like dimming. They produce something that's closer to a sinusoid. So the shape is wrong and the time scale is wrong is the basic answer. Okay? So this is Kepler 10b, only 40% bigger than the Earth, an incredible orbital period of less than a day. Following up on this discovery by the Kepler Space Telescope, Jeff Marcy, who you'll hear from in the last talk, and I and several others used the Keck telescope on Mauna Kea to measure the mass of this planet. And if we had a 2-hour talk, I would explain in detail about how we do all these mass measurements, but I don't have time for that. Maybe a 2-minute version of the questions if you guys are interested. But we see perfectly in phase with the light pattern of the planet, we see this motion of the star as it's being tugged on gravitationally by the planet, and the amplitude of this gravitational tug tells us the mass of the planet. When we take the radius of the planet from Kepler, the mass of the planet from the Doppler effect, we can compute a density, and we find a density which at the time I made this plot was about 9 grams per cubic centimeter. It's since then been revised downward a little bit. But this is still a high density. This indicates this is likely a planet made of solid materials. Another way we can see that same point, that this is made of solid materials, is to plot the ensemble of planets discovered by Kepler and other missions and surveys on a 2-dimensional domain of planet mass on the horizontal axis and planet size on the vertical axis. In this plot, the solar system planets are in green, so Earth and Venus are right here to kind of anchor you. Here's Jupiter and Saturn. Uranus and Neptune are up here. And these blue solid lines are what I like to call mathematicians' planets. If you took a pure composition and just made a ball of that material, that's the size and the mass curve that you would get. So we know that Kepler 10b is in this domain of rock and iron, and it's probably made of some combination of the two of those. We also know that since it's so close to its star, it's hot, probably about 1,500 or 2,000 degrees, so it's unlikely to have a significant hydrogen atmosphere. It would simply be cooked off. So, go ahead. So what I've drawn here, this is a diagram that a geologist would be offended by. It turns out what I've called rock here is actually MgSiO4. If you plot MgSiO3, it differs by about the thickness of the line. So we just call it rock. This one particular planet, Kepler 10b, is part of an ensemble of now thousands of planets which have been discovered. Only a handful of them have had their masses measured. But we can also plot this ensemble of planets in a new domain. In this domain, we have planet size on the vertical axis. And again, here's Earth size, here's Neptune size, and here's Jupiter size. But now on the horizontal axis, instead of planet mass, we have planet orbital period. So you can think of this basically as a proxy of distance from the star. The two are period and semi-major axis are, of course, related by Kepler's third law. So here's a 1-day orbit. And here's where Kepler 10b sits. It's a little bit bigger than the Earth and a little bit shorter than 1 day. It's not a terribly common planet, but it's not 1 in a million either. And so this huge ensemble of discovered planets from Kepler provides a way to do a census of the planets orbiting other stars. To do this census properly, we have to take account of all the ways that Kepler can miss planets, that it can fail to discover a planet. Many of the stars which Kepler looks at have planets, but they're just undiscovered. And there's a few reasons for that. One is that many of the orbital planes of the planet are not aligned to Kepler's line of sight. They're simply tipped out of view, and Kepler has no idea that there's a planet there. That's actually the majority of the cases. Kepler has to look at a couple 100,000 stars if it wanted to detect a few thousand planets just due to geometry.
The ratio still be the same?
The ratio is the same.
The chart would look the same.
Yeah. Well, no, it wouldn't actually. In any given orbital period, it would. The farther you are away from the star, the lower your chance of transiting that star. The Earth has a lower chance of passing in front of the sun from a distant observer than does Mercury. So, in fact, this tailing off that we see fewer and fewer planets as we go to longer and longer orbital periods is in large part due to this effect. Okay? So if we take account of the effect I just mentioned, this geometric effect, and the effect that smaller planets are hard to find in the real-life noise of the Kepler photometry, sometimes you can't actually see the dip, it's just blended into noise. If you take account of those two statistical effects, we can compute the underlying, the intrinsic distribution of planets that are actually in nature. Accounting for those effects, we determine what we actually observed with the Kepler Space Telescope. So this plot has the same axes. This is planet size on the vertical axis. Here's Earth size down here, and here's orbital period on the horizontal axis. And the color coding here denotes planet occurrence, the prevalence of planets. Red squares here have very high planet occurrence. Blue have very low. And the range here is actually substantial. These planets are about 1,000 times more common in nature than are these highly unusual planets up here. And one of the main lessons from the Kepler mission is that there is a domain of planets, which we call super-Earths, sometimes sub-Neptunes, that are the most common type of planet in the galaxy, at least orbiting close in, and somehow we don't have one in our own solar system. So this was quite a surprise. This new planet types, which we call super-Earths, sometimes sub-Neptunes, they're great fodder for graphic illustrators and science fiction and so forth. We call them super-Earths, but this is really kind of a gimmicky name that we use mostly for proposals that we want to be funded. And in fact, I kind of doubt they all have blue oceans and white clouds and continents and so forth. They're in fact much more diverse. This is probably more of a typical view of one with substantial clouds. So going back to our view of planets in this size versus mass domain, remember here's Earth and Venus, here's Neptune and Uranus, and this domain in between is the domain of the super-Earths and the sub-Neptunes. And you can see that it crosses through these major composition contours. So you can actually have these planets could be made of various combinations of hydrogen or even hydrogen-helium, water, rock, and iron. And we wouldn't really know the difference if we're only measuring these basic properties of mass and radius. And in fact, when people make very detailed models of them, these are models that were constructed for a particular planet that has very well measured size of 2.9 times the size of Earth and a very well measured mass of 6.4 times. These are just three of the kind of ensemble of planet compositions that are consistent with those measurements. So in the next 5, 10 more years, one of the major goals of our field is to try to understand what is the actual composition of these planets. Are they super comets that are half water, half rock iron? Or do they have hydrogen or hydrogen-helium atmospheres that make them extended and tenuous for a given mass? We don't know yet. We're starting to get some clues, but this is a major question moving forward. One of the other things that we can probe about sub-Neptune-sized planets is we can measure their density. Density, of course, is a pretty good first-order measure of a planet's composition. The Earth has a density of about 5 grams per cubic centimeter, and the gas and the ice giants have densities on the order of 1 gram per cubic centimeter. So just on that, you can say something about the primary constituents and the extent of the atmosphere. And when we plot density, it's shown here on the vertical axis as a function of planet radius, we see a very interesting thing. As the planets get smaller and smaller, they go from being very commonly a gram per cubic centimeter, which is consistent with the ice giants and the gas giants, and their average density starts to rise. There's still very substantial scatter about this curve. Some of these planets are low density, some of them are high density, but nevertheless the average increases, and it reaches a peak at about 1.5 times the size of the Earth. One interpretation that I like of this rise is that we're now beginning to see planets that have little or no atmosphere. I would say the Earth actually has little or no atmosphere. The Earth does not have an atmosphere that contributes substantially to its radius, as seen from very far away. If you go to planets a little bit smaller than this decrease in density can simply be due to the same composition planet, but having reduced compression. It turns out the Earth, with its density of 5.5 grams per cubic centimeter, has a density that is somewhat higher than it would have if it were uncompressed rock. If you took all the pieces of the Earth and spread them out and measured their densities separately, you would find that it's something like 3.5 or 4 grams per cubic centimeter. So the same material can produce a lower density if you have a lower overall mass. And then we have this idea that as you go to larger planets, I've said this already once, but I think it's good to illustrate it graphically. At the peak of this curve, we can imagine having a silicate mantle surrounding an iron or perhaps an iron-nickel interior. And as you spoon on just relatively small amounts of gas, small amounts by mass that is, you can swell the size of the planet substantially, retaining the same core on the inside. So one explanation for at least the kind of middle of this curve is that as you move to the right, these planets simply have more gas. They may not be substantially heavier. Okay? So now let's take a step back and look at some of the other interesting planets that Kepler's discovered from this domain of size and orbital period. I talked about Kepler 10b, which was right about here. An even more extreme planet, the one that I'm especially attached to, is called Kepler 78b. If you thought Kepler 10b had a short orbital period, you'll think this one is even more impressive. Its orbital period is 8 hours. And it turns out that its size is almost exactly that of Earth. It's 1.2 times the size of the Earth. So this presented a really remarkable opportunity. Kepler had discovered a planet approximately the Earth's size. Using the Keck telescope in Hawaii, we measured the mass of this planet. And when you put the mass and the radius together, here's a little diagram of what this thing might look like. You can imagine in an 8-hour orbit, it's baked to a crisp. It has an equilibrium temperature of about 2,500 degrees. We can't actually measure that temperature, but that's just based on an estimate as to how close the star is. If you're on the surface of this planet, the star would subtend something like 80 degrees on the sky. Yeah. This star is a little bit younger than the Sun, and it's a little bit less massive. Its mass is about 8/10 the mass of our Sun. So what's remarkable is Kepler 78b is, at least in bulk properties, a scaled-up version of the Earth. Mass, of course, scales as the cube of the radius, and if you cube 1.2, you get 1.7. So we can say right away that this planet has essentially the same density as the Earth and likely a very similar composition. Okay, Kepler 78b is nice, but what about planets that have blue oceans and white water clouds and nice destinations? What about planets that have Santa Barbaras on them? To find a Santa Barbara-like planet, we need to be in the habitable zone. Now, some of you, I don't know if anybody came from the interior of the country, that we might call that not the habitable zone, but the habitable zone, as a general concept, is the set of orbital distances where the planet could sustain liquid water on its surface for some time. If the planet is too close, the water is boiled off and it becomes a steam atmosphere and you never have surface liquid water. Too far and you get a global ice age and you never have surface liquid water. Yeah?
What about the case of a planet with a very eccentric orbit so that it passes through the habitable zone but has, ice ages and hot times?
Yeah, so the question is about what about an eccentric planet that takes a path through all of these zones, something like this. The answer there is it's more complicated. Depending on what kind of atmosphere it have, it might serve to average out the weather a little bit. I think in most cases this probably wouldn't be a place you'd want to live. But you can imagine maybe an intermediate case of a planet that's mostly in the habitable zone and occasionally it peaks out into the too cold zone. In that case, it'd be very difficult to predict in advance. It would probably depend on the details of the planet's atmosphere. So this concept of the habitable zone is a nice one. It encompasses the Earth. We have trouble figuring out exactly where to draw these lines, and I'll come back to this idea of definition of the habitable zone at the end of my talk. But I wanted to highlight at least one of the discoveries of a planet in the habitable zone by the Kepler Space Telescope. This planet has the name Kepler 186f. Kepler 186f is remarkable in one of these multi-systems that has 5 planets, all of which transit. So remember, these is a kind of record-thin planetary system. All of the planets pass in front of their star as seen by us far away. This planetary system is especially detectable, the habitable zone planet is, because these planets orbit a relatively cool M-dwarf star. And because the star is cooler, the habitable zone has to be closer in. Those orbits take shorter periods of time, and so Kepler is able to detect a planet in the habitable zone of the star. So our friends and the NASA Outreach Office have created a very nice animation of this system. It starts with a top-down view of Kepler 186. You can see that there's 4 planets. These planets in the interior, and in total, these planets range in size from 1.1 to 1.5 times the size of the Earth. And you can see these planets are kind of nicely going around. Now what will come into view is Kepler 186f. This is where the speculation begins. Kepler 186f is the planet which is the smallest one. It's 1.1 times the size of the Earth. And it is, in fact, in the habitable zone. Forget how long these animations go.
How many light years away is it?
Natalie, do you remember?
I want to say 500.
500. That sounds about right. Yeah. Most the typical faint star in the Kepler survey is about a kiloparsec away, 3,000 light years. The really bright ones, or the M-dwarfs, which are fainter but have to be intrinsically closer to be seen by Kepler, those are a factor of several closer. So if you want to think about the size of the habitable zone of this planetary system, Kepler 186, compared to the habitable zone in our own solar system, it looks something like this. The star, of course, as I've said, is less luminous, so the planets have to huddle closer if they want to stay warm. One of the nice bits of kind of daydreaming you can do about planets like this is to think about what a sunset would look like on Kepler 186f. The star is cooler and redder, and so you would have a sunset which is intensely red due to the intrinsic color of the star and not due to small particle scattering in the atmosphere of the planet and the fact that the blue rays had been really scattered away. It would just be really impressive. Okay, so Kepler 186f is a remarkable system. Let's now talk about how common these systems are in general. This is a similar plot to one that I've shown before, and this is another representation of the distribution of Kepler-discovered planets as a function of their size. And previously I had plotted orbital period here, but now I'm reframing the problem and plotting it as a function of so-called stellar light intensity. This is essentially the brightness of the star that the planet sees from the position of the planet. So a stellar light intensity of 1 is at the Earth. If you're at half an AU, the brightness is a factor of 4 higher because the sunlight falls off like 1 over r squared. So here's all the red dots are all the planets that have been discovered. These blue contours tell you how difficult it is to discover a planet at that particular planet size and distance. Blue is where we have no hope at all. These planets are just completely buried in the noise. The white domain is where we should be able to detect every single one of them unless their orbital plane is tilted out of view by geometry. So we can draw a box in this domain and compute the underlying distribution of planets that occur in nature and try to assess how common Earth-like planets are. Well, I've drawn a box here that has a size distribution going from Earth size all the way over here to 2 times Earth size. We'll call that approximately Earth size for now, and we can debate whether or not that's a good definition. And then in the horizontal direction, we have a box which extends from the same flux as the Earth to a factor of 4 less and to a factor of 4 more. And using this box and making all the statistical corrections, what we find is that the underlying occurrence, the underlying prevalence of planets, is about 22%. So 22% of sun-like stars have a planet that is roughly the same size and the same temperature as the Earth. That's a pretty impressive number. I like to think of it as you look up at the night sky and start counting stars. Every 5th star has a planet with those characteristics. This was work that was combination of effort by the Kepler team and by Eric Pettigura, who's a graduate student at Berkeley, Jeff Marcy, and myself. And when we did this calculation, we commissioned the creation of a short little, this is a 30-second little movie to summarize this discovery. And since we paid for this movie, I'm obligated to show it to you now. So I'll briefly animate this, and this kind of encompasses the whole idea of the entire Kepler mission and this discovery. And by the way, you can download this off the internet if you'd like. So I'll start the movie. So Kepler searches for stars between Cygnus and Lyra, and if we zoom in on one particular star, we're looking for planets that are in the habitable zone. We've discussed this concept already. These planets are not too hot and not too cold. They're just right. And we searched for planets that were in the size range of 1 to 2 times the size of the Earth. If you randomly select 20 stars observed by Kepler, we would expect that about 4 of them would have these kinds of planets intrinsically that are the right size, approximately the same size and the same temperature as the Earth. In other words, 1 in 5, or 20% of sun-like stars, have these habitable zone Earth-sized planets. Okay, so that's a very nice result. I've brushed a few things under the table to provide this kind of this dramatic result. One of the things that I brushed under the table was the size distribution of Earth-like planets. I just asserted that planets 1 to 2 times the size of the Earth are Earth size. We saw earlier in the talk that there's probably a significant change in planets at about 1.5 times the size of the Earth. So maybe that definition isn't actually right. Turns out that recent work of 1.5 times the size of the Earth came after we had this earlier paper, and maybe we would have chosen a different range at the time. And I would also imagine planets that are smaller than the Earth have some possibility of being Earth-like, terrestrial, potentially having other Earth-like characteristics. The truth is we don't quite know. Yeah, question?
When you say sun-like stars, you mean G8 stars, or what range of stars are you talking about?
So this survey encompassed all G and K stars. So this is a temperature range of, I believe, 4,000 Kelvin to 6,000 Kelvin. The other domain that I've kind of brushed under the rug is what is the range of stellar light intensity, what is the range of flux received by the star that is consistent with the habitable zone. And I just asserted that if the planet received flux within the factor of 4, that we could call that the habitable zone. That's probably a dramatic oversimplification of the problem, and this is actually an active area of research to figure out what the boundaries of a habitable zone are. This habitable zone concept is shown in a little bit more detail in this nice plot from a review article by Sarah Seeger. And in this plot, this is orbital distance here, and basically an AU. So this is 1 AU right here. And the vertical axis, this is mass of the star. So the sun is right here. And the way you read this is you draw a line across this plot. That's how you find the habitable zone for our solar system, where it intersects these various colors. For cooler stars, the habitable zone is closer in, and so the intercepts are a little closer. Hotter stars, the intercepts are farther away. There's been a lot of debate, especially in the past few years, about the definition of the habitable zone. A kind of traditional definition of the habitable zone, which basically involves creating a simplified climate model and moving the Earth into different orbital positions and asking, would we lose the Earth's atmosphere to photolysis on the inside, or would all of the water freeze out into a giant snowball Earth on the outside, and asking, what are the boundaries of that orbit? And you can calculate these boundaries. This was done by Jim Casting and more recently by Ravi Kaparapu. Here's where this inner edge of the habitable zone is. I find it kind of remarkable that in this calculation, the Earth is basically at the inner edge of the habitable zone. It's within a couple hundredths of an AU by this definition. The outer definition corresponds to where you can basically pump up the maximum CO2 greenhouse to keep the oceans from freezing. And that definition leads to a habitable zone boundary that's a little bit past the orbit of Mars. As I said, this is a controversial topic. Others have said, wait a second, we don't have to choose exactly an Earth-like planet that has exactly the concentration of water, CO2, nitrogen, and other species as our own Earth. What if we consider a planet that has, for example, an extremely low humidity so that the water-based greenhouse effect is minimized? And what if we make the planet's surface have high reflectivity, we increase the albedo? We can push such a planet closer to the sun, and it's able to get rid of its heat more efficiently. And so these calculations suggest that you could, in the extreme case of a planet that's exactly tuned to this getting rid of heat property, you could get all the way down to 0.38 AU. How far could you get in the other direction? Well, if you want to stay warm as you move farther and farther away from the star, you have to find an extremely efficient greenhouse effect. CO2 greenhouse could keep the Earth warm potentially slightly to past the orbit of Mars. If instead the Earth had an H2 atmosphere, it turns out that there's an extremely broad collisionally induced absorption feature in the infrared part of the spectrum that acts as a massive greenhouse for an atmosphere which is dominated by H2. So push the Earth out to Saturn's orbit, it would freeze solid. But push a planet that has an H2 atmosphere out there, and potentially you could have a heavy greenhouse effect that could keep it warm out to those distances. So you can see that to some extent, actually to a large extent, the habitable zone depends critically on the nature of the planet's atmosphere. Our own Earth probably has a more modest habitable zone, but around planets of different compositions and different atmospheres or on different stars have their own habitable zone. Interestingly, this kind of H2-dominated planet, if you pushed it in, it would be unimaginably hot even at these kind of modest distances because the greenhouse effect would really heat it up there. So I want to finish my talk by kind of segueing into one of the next few talks by just describing some of the remarkable characteristics that our Earth has. These are, you might call these kind of anthropocentric arguments about why we're here. I have a long list which I'll kind of briefly go through. The Earth, life on the Earth benefits from the fact that we live around a star which has survived for billions of years and is relatively outburst-free. We live on a planet that actually has a surface. It's not obvious that chemistry of the origin of life would begin if there wasn't a surface. Many of the reactions that are thought to facilitate the origin of life require mediation on a surface just so that the complex molecules have some finite chance of interacting. The atmosphere of the Earth seems to be just enough so that, for example, it shields UV light. It's relatively low density. It's an atmosphere and not an envelope. If you think about Neptune and Uranus, they have envelopes and not really atmospheres. There's no solid atmosphere interface on those sorts of planets, because by the time you get down to those depths, you're at such extreme pressures that the astrophysical ices are in really weird states, not the liquid water or liquid ice or water ice phases that we would consider today. I know Jeff's going to talk about this in some detail, and you heard Sean talk about it. It's kind of remarkable that we have seemingly just the right amount of water so that we have both oceans and continents. A little bit more, a few oceans more water, and we wouldn't really have continents. The temperature is just right. We spent some time talking about the habitable zone. The Earth's orbit is nicely circular, and this, as the gentleman in the front said, keeps us in the habitable zone at all times, and we don't venture out of it. And then there's a couple other characteristics that I want to describe. One is that the Earth has a relatively large moon that stabilizes the obliquity of the Earth. If you take the Earth at its current rotation rate, remove the moon, and ask what is the evolution of that system, it undergoes chaotic obliquity fluctuations. It does not stay at 23.5 degrees from the sun. It wobbles all over. So perhaps we need a moon to stabilize climate. Another interesting property is that we have Jupiter in the outer solar system. Jupiter acts basically as Eric talked about, it dynamically gathers up many of the small bodies which come in from the outer solar system and which could potentially be harmful to the Earth, comets especially. So these are some of the incredible characteristics of the Earth. I want to offer a little bit of a word of caution. This is somewhat of a traditional list. I don't actually agree entirely with this list. And I'll tell you two of the characteristics which I think are commonly cited as evidence that we're in a lucky system, and maybe it's not quite that way. The first one is this idea of a large moon. So it is true that the Earth, with its current 24-hour rotation period, would be unstable if you remove the moon. But you have to also ask, what would happen if the moon was never there to begin with? If the moon was never there, we probably would have a substantially faster rotation period, something on the order of 6 or 8 hours. And it's likely that as the moon formed, as it spun out, this exchange of angular momentum slowed down the Earth's orbit. And so we have to ask the question, would the Earth be stable against chaotic obliquity fluctuations with a 6 or 8 hour orbital period, with perhaps what its intrinsic one is? And the answer is yes. So maybe the moon doesn't matter. Maybe it does in some unappreciated way. Jupiter is another example. Jupiter acts as a very efficient vacuum cleaner for material from the Kuiper belt. But the Kuiper belt wouldn't exist in its current form if Jupiter hadn't pumped all that material out there with high eccentricity and inclination. So maybe we don't need a Jupiter for the emergence of life on the Earth. So I think remarkably I've finished a minute ahead of time. And we have 16 minutes for questions. So thank you.
Wonderful. Thank you for that talk. We've got lots of time for questions and discussion. I'm sure there's lots of compelling questions we could ask him.
While you're on that slide, you talked about unusual phases for large planets as you go down through the atmosphere. Could you expound on that a little bit more?
So the question was about these unusual phases. So if you look at let's take water, for example, H2O. The three phases we're familiar with are steam, liquid water, and ice. And if you plot them on a temperature pressure diagram, they have some well-defined characteristics. There's a triple point, critical point, etc. As you go to much higher pressures, though, you get changes in the solid ice form, crystalline changes, that lead to many different phases of ice. And it turns out there's about 15 phases of ice which have been probed, which have been measured experimentally. And these ices have properties unlike the materials that we're used to. Some of them occur at relatively high temperatures, and so as you probe down lower and lower in a planet's envelope, you don't transition directly into a solid material to, say, a silicate mantle. you first go through all of these weird phases. And to me, it seems that the organic chemistry of life is very unlikely to exist in those very high temperature, especially those high pressure phases.
I tell my kids there's 5 phases of matter. That's just one more lie that I'm telling you.
I guess so. Yeah.
What are the possibilities for heat sources other than the sun for the planets that might enable it to be a habitable planet?
So in our own solar system actually provides a couple of really interesting examples. And this encompasses a broader definition of the habitable zone. The one that I've described is a very star-centric habitable zone. In our own solar system, the moon of Jupiter, called Europa, orbits around Jupiter, and it has Europa has a water ice shell with approximately a 10-kilometer thick salty water ocean, and then basically a silicate mantle beneath that. And the orbit is slightly eccentric. The eccentricity is driven by a resonance with the other moons of Jupiter. And as that eccentricity is dissipated through tides orbiting Jupiter, this heats up Europa and is likely what keeps the ocean in liquid state. So tides are one example. Another example is radiogenic heating. So these are radioactive isotopes that decay at such a rate that they heat the interior of the planet. That heat has to escape. The flux of heat that emerges from the interior of the planet heats the surface. The radiogenic heating on a kind of billion-year time scale is probably not sufficient, but on a relatively short-lived time scale, it is. I didn't include this slide in this particular talk. One thing I especially like is I'm not a science fiction fan per se, but I was browsing the science fiction literature, and I saw that somebody had written a book about life on a super Earth, which is kind of nice that they're encompassing all of the new discoveries. And this super Earth was relatively young. It was less than 1 billion years old, and it was it was basically a slave colony for mining uranium-235, and it was radiogenically heated to very high temperatures. So there's an example of life on such a planet. So maybe my colleagues in the audience can help me if there's other examples I've forgotten besides tides and radiogenic heating.
So I'm thinking like my students now, and what is the closest Earth-like planet in a habitable zone?
If you take the calculation that we did of 1 in 5 stars like the Sun has a planet that's the same size and temperature as the Earth, and ask what is the nearest Sun-like star that has those characteristics, it's about 12 light years away. We don't know the name of that star, but
I know we've been focused more on planets, like what are the requirements? Are there any constraints on the star? Like which kinds of stars can support habitable planets?
That's a really good question. There's a lot of research now on M stars. M stars are these are the red dwarfs that are smaller, less luminous, cooler than our sun. And so seemingly you could just shrink the habitable zone down in closer. We don't know if that's going to work because these M stars are more commonly have flares and outbursts that produce intense X-ray and UV bursts, which you could imagine if such a burst hit the Earth, could remove a substantial fraction of the ozone from the Earth's atmosphere. So it's unclear if planets in such systems would be stable over geological time against such injustices from an M-dwarf-like star. You could imagine maybe you don't have the Earth's atmosphere there, you have some other kind of atmosphere, or you have life that's subsurface and is insensitive to such things. But I'd say this is one of the considerations that people take account of. Moving outwards from the star, I don't know of any particular limitations that if you make the star more luminous and the orbits just keep expanding, I can't think of anything that makes it less likely to support life. provided you have the right planet and atmosphere and so forth.
Let's see, back here.
Wouldn't there be an upper, well, no, I guess not. I was going to say an upper limit on the size of the star because they don't last very long, but I guess that would just limit the evolution of the life. So.
Yeah, I mean, if we get to a few to several times the mass of the sun, these stars only live for 10 million years, much shorter than the evolution of life. So that is an important limit, a timescale limitation.
I'm curious about not planets, but say life, simple forms of life evolving on comets or asteroids or other small objects that are in the habitable zone or come in and out of it and allow bacteria to go dormant or something sort of more oddball but much more numerous.
It's a very interesting possibility. I'd say it's speculative. One, and if you'll allow me to speculate a little bit, one thing that I think perhaps led to the emergence of life on Earth was that we had such a large volume for chemistry to try out different combinations so that first cell could get going. And so perhaps the probability is proportional to the volume of the planet. We probably also want to have a body which is large enough so that the entire body goes through a phase where it melts and you have a mixing of materials so that chemistry isn't localized just to little individual grains. That size is on the order of a couple hundred kilometers. These are the size of kind of the medium and large asteroids.
So do you think that we have a hope of finding this Earth-like planet within 12 light years?
We didn't plan this. I swear we didn't plan it. Right, Natalie? So, oops, I'll go back. Can we detect an Earth-like planet? People are working really hard to figure this out. There's some study teams at NASA in particular that are working hard to find this out. Taking a picture of an Earth-like planet is very difficult. It's analogous to searching for a person with a lit match standing at the base of a lighthouse. So there's a huge contrast problem, something like 10 billion to 1 if you're using optical wavelengths. And the lighthouse is in Hawaii and you're in California, and you have to resolve this incredibly small angle in between. So how do you solve the small angle problem and the contrast problem? One proposed solution, this is only one of a couple, and I like it especially because it makes for a very nice movie, is a starshade mission. So the idea is you have a telescope in orbit out of the Earth's atmosphere, and it looks at the planets behind a starshade, which is allowed to drift a couple tens of kilometers away. And this very funny shape, these weird petals on the starshade, have this very precise mathematical form to suppress the diffraction around the starshade. They have this just so shape. And it turns out that you can, to a factor of something like 10 to the 10, maybe 10 to the 11, you can suppress scattering and diffraction around the edges of this starshade. And as the planets orbit their star, they peek out and then go back behind. That's the idea anyway. We don't have real movies like this yet.
Any other questions for Andrew?
Speaking of other missions, what are the prospects for the TESS mission for looking at transits around other stars?
Yeah, so the Kepler mission was enormously successful, just to give everyone a little bit of background, which you probably have. And Kepler was the mission I talked about. It operated for 4 years. After 4 years, 2 of the 4 reaction wheels on Kepler, these are the gyroscopes, the powered gyroscopes that keep Kepler pointing in a fixed direction, 2 of them failed. And Kepler could point precisely in 2 dimensions, but not a third. And so it was basically kind of wobbling and unable to point at that same star field. There's a new Kepler mission, which has been operating for about a year now, called K2, which takes advantage of a very clever engineering trick by Natalie and her colleagues at NASA Ames. And they realized that you can stabilize the Kepler telescope in one dimension because it has two giant wing-like structures on it, which are its solar panels. And so if you position the solar panels so that they receive the same amount of sunlight, that's the primary thing that applies a torque that causes it to turn, you can balance on the head of a pin in one dimension for about half a day. And so you use the gyroscopes to stabilize the other two dimensions and sunlight to stabilize the third. The geometry forces you to look along the ecliptic. And so this K2 mission has 13 fields, each of which, in each field, it's a pointing in one part of the sky. It spends 75 days pointing at each part of the sky, and then it has to move on because K2 is moving. So that's what's happening with Kepler. The TESS mission will launch, I believe, in 2017, so now only 2 years away. TESS is a successor mission to Kepler, new telescope. Whereas Kepler looked at 100 square degrees, it's 1/400th of the sky. TESS has a much bigger array of CCDs, and it will look at a large swath of the sky, stare at that swath for 30 days, step around the northern hemisphere, observe the entire northern hemisphere, do the same thing in the south, and thereby discover probably all of the interesting short period transiting planets that we'll ever know. Those transiting planets will be great to follow up with the James Webb Space Telescope, with telescopes on Earth where we can measure masses with the Doppler shift. So that's the whole purpose of TESS. That's all the background to get everybody else up to speed. The update is TESS is doing beautifully, and the last I heard, it's on schedule for a launch in 2017.
With all the developing technologies in astrobiology that have come about in the last 30 years or so, especially in the last 15 years, do you see a redefinition popping up of the 21st century Drake equation?
I know that one of our later speakers is going to talk about the Drake equation in depth. Okay, 2 later speakers. So perhaps I'll leave it to them.
Any other questions? Let's see.
Okay. I have a general question. Both as a student and as a faculty, when I teach or learn astrophysics, we feel that planetary science is relatively known, and we move to black holes and all those exotic matter. But it looks like with these exoplanets, the basic understanding of our solar system is being questioned. So could you comment on how we view our previous understanding in the context of data that we have got from exoplanets?
The way I like to think of it is that solar system astronomy is a 400-year-old science, even longer, before the invention of the telescope. And we've reached a mature state where we're arguing about details of individual objects. What extrasolar planets do is they provide a context for all of those details. For any one of these extrasolar systems, we're probably only going to learn the basic characteristics. But we can do that for thousands of systems. And so we can see where the Earth fits and where the solar system fits in that continuum. So that's how I guess I'd say that the two fields are connected.
So larger data system that we have instead of just focused on solar system.
Yeah, we're zooming out from our one example. And I would, I'm not in a planetary science department, and I'm not particularly a planetary scientist in the traditional sense, but I guess I would say that field is very alive and well with many active problems that are being worked on. So, any other questions?
Yeah, you said earlier in the talk, if you had 2 minutes, you'd talk about how to find the mass using the Doppler shift.
Okay. I don't have slides, but I'll explain it. So the question was, how do we measure the mass of a planet with using the Doppler method? Here, this is an indirect technique. We do not actually observe light from the planet itself. The planet is in orbit around the star. And in fact, to be more precise, the planet and the star are in orbit around their common center of mass, the size of the planet's orbit relative to the star is the ratio of the masses. So if you can measure the orbit of the star, you can infer the orbit of the planet. And we do this by measuring a one-dimensional projection of this motion. We measure along the line of sight, the radial direction. And we don't actually measure the radial position of the star as a function of time. We measure its first derivative. We measure the so-called radial velocity of the star. We measure the radial velocity using the Doppler technique. So as the light is Doppler shifted blueward towards us, we know the star is approaching us and it has a positive radial velocity. And so with many measurements of the radial velocity over time, it will take on some shape. For a single planet, that might be a sinusoidal shape, which indicates a planet in circular motion. And you can deduce the mass of the planet by the amplitude of this radial velocity wobble. An eccentric planet produces a non-sinusoidal shape, and you can tease out the nature of an entire planetary system, including one with more than one planet, just by analyzing this series of measurements. So all of these measurements are made with precise Doppler spectrometers, which are instruments on small, medium, and large telescopes all over the Earth.
What's the resolution of radial velocity currently?
The radial velocity work is around 1 meter per second. Jeff Marcy and I in the back are working on a new instrument, which we think will push down even further to about 0.3, 0.5 meters per second. Other people have designs on other instruments which will do similar. In some cases, they claim better. So it's an exciting time. Oh, are we done, or do you want to?
I think we've run out of time,
Okay.
but do feel free to ask
catch up in the
Andrew
break.
some questions during the break. We've got a break now for 30 minutes. We'll reconvene, and the next talk will start promptly at 3:30. Let's bring our speaker again.